first thing you're asked to do with this problem is to draw a vector representing the normal force. Now the normal force is going to have the same magnitude as the weight force. We know that because the box isn't sinking into the ground and it's not flying up into the sky. So we need to draw a vector vertically upwards for the normal, but it needs to be to scale. We're told that the scale to use is that 1 centimeter equals 4 newtons. So we need to take that 20 centimeters, or sorry, the 20 newtons. We want to get rid of newtons, so we're going to say 4 newtons on the bottom equals 1 centimeter on the top. And that is going to give you a length that is 5 centimeters. Then what you're going to do is you're going to take a ruler and you're going to draw a straight line upwards to scale, and it's got to be 5 centimeters long. So that's the first part of it. 62 asks you to calculate the magnitude of the friction force. To do that, we're going to use an exciting equation, the fun equation, F equals mu n, keeping in mind that this normal force, under many circumstances like this, where it's flat, is going to be equal to the weight force. It isn't always, but for a problem like this, it is. So we're going to need to look up the coefficient of friction for wood on woods. This is wood, this is wood. So you need to go to your reference table on the first page, scroll down, and here we're doing wood on wood. And because the box is moving, it's going to be the kinetic coefficient of friction. So the coefficient of friction we're going to use is going to be 0.3. So we can go ahead and we can plug in for that. 0.3. Remember, coefficient of friction is the ratio. It's how many times, what fraction of the normal force you need to apply to get this thing to move, or in this case, keep moving. The normal force we're given is 20 newtons. So the friction force, 0.3 times 20, is going to give you 6 newtons. So that is the magnitude of the friction force. Now, to determine the magnitude of the net force, there are 2 definitions of net force. F net equals ma. Comes in handy sometimes. Here, we're going to use the other definition of net force, which is that the net force is equal to the sum of the forces. So you add up all the forces, however many there may be, acting on an object, and you add them up. You have to keep direction accounted for when you do this. So if this is a free body diagram for the box, you have an applied force, which you're told is 8 newtons, and you have a friction force, which must oppose that motion, which we just figured out is 6 newtons. So the F net here is going to be the applied force minus the friction force. It's going to be 8 newtons minus 6 newtons. That net force is going to be 2 newtons. Now to calculate the mass of the box, there you're going to use the definition of weight. Weight force is the mass times the acceleration due to gravity. Weight force, 20 newtons, equals mass times 9.8 newton, or no, sorry, 9.8 meters per second squared. Divide, and you are going to get a mass that is 2.04 kilograms. And finally, to get the acceleration, once you have the net force and you have the mass, we're going to use the other definition of net force. That definition is that F net equals ma, or the way it's presented on the reference table, is the acceleration is net force divided by mass. So you're going to take that net force of 2 newtons divided by the mass, which we'll say is 2.04 kilograms, and when you divide that, you're going to get an acceleration of 0.98 meters per second squared, which is your final answer. So that was a fun problem. At least it was for me.